So the extensive research and design that goes into making today's rings dependable and durable isn't obvious. But think of it this way. At 3,600 RPMs, these pistons hit top dead center 60 times each second, which means the rings change direction 120 times each second. And each time a ring changes direction, it exerts considerable force on the sides of the ring grooves. Finding ways to reduce this ring inertia force by reducing mass is a big challenge when designing smaller, more fuel-efficient engines. For every 1,000th of cylinder bore taper, a ring must open and close over 3,000ths at the gap. Even tiny tolerance changes can multiply into a great effect on ring performance. Yes, rings have some big jobs to do. And to do their jobs, they must work in an environment where all engine parts and support systems are in good operating condition. Of course, good sealing is the main job of the compression rings. On the firing stroke, the top ring should keep as much of the combustion gases above it as possible to assist in pushing the piston down. What gets by the top ring should be picked up by the second ring, because whatever gets past it to the crankcase is blow-by, which represents wasted power. The oil ring meters a controlled amount of oil to the cylinder wall to reduce friction, prevent scuffing, and help sealing, then returns the rest to the crankcase. The second compression ring also backs up the oil ring on oil control. If oil gets into the combustion chamber, it creates combustion problems, loss of power, and a smoking engine. Compression rings not only have to seal against the cylinder wall, they must prevent blow-by getting through between the ring and the piston groove. From its relaxed position on the intake stroke, the top ring is flattened by gas pressure against the bottom of the piston groove and pushed out against the cylinder wall. When it can't do this, it must be replaced. There are two critical ring wear areas, the face and the underside. As the piston moves up and down, rubbing action between the ring groove and the bottom surface of the ring gradually develops a wear step. Just a few 10,000ths will open a path for blow-by. The 5/64ths regular iron torsional twist top compression rings we have been using for years in most passenger car engines are slowly giving way to narrower, lighter compression rings. This is raising some challenging problems. Most top rings are now faced with molybdenum. Moly's higher melting point and oil-carrying capacity gives better resistance to scuffing than plain iron or chrome. Under a microscope, you can see the surface voids which carry lubrication and provide a place for wear particles to go. Electroplated chrome facings are used for most tractor and heavy-duty top rings. Chrome is harder and has less porosity than plain iron or moly, so it wears well and stands up better under dusty or dirty conditions. Of course, dirt is the enemy of cylinders and rings. A normal fuel mix is 10,000 to 1, which is a lot of air for 1 gallon of fuel. It is said that if you have a 1/16 inch diameter leak anywhere in the air intake system, you just as well not bother installing an air filter.